Welcome to another video session for the UPH004 Applied Physics course. In this session, we'll talk about diffraction, the tutorial sheet number 6. So this tutorial sheet includes the problems of single slit diffraction, double slit diffraction, and diffraction grating. So let us look at this first problem. For a single slit diffraction fringe, find the percentage intensities of the first and second order maxima with respect to that of the central maxima. So let's go back to our worksheet. So here is the first problem. Now to start with, let us look at the single slit diffraction pattern expression. So here is the intensity is given by sine square beta by beta square, where beta is equal to pi b sine theta by lambda. And this, if you plot versus theta, this plot looks like, so there is a central maxima and then there are secondary maxima as you go away from the center. So this is maxima and these are called secondary maxima. So n is equal to 0 is the central maxima, n is equal to 1 is the first order maxima, n is equal to 2 is the second order maxima, and so forth on the left hand side too. This is a symmetric intensity distribution. In this direction it's the intensity and this much is I naught. So what is then percentage of the intensity at the second maxima with respect to the percentage of the central maxima? Now to do that, first what you have to do is find out what are those positions where you have maxima. How to do that? Then you take the derivative of the intensity with respect to the beta and equate that to 0 to find out the maximums. When you do this, then you would get, and from here you can say tan beta is equal to beta. So this becomes a condition for finding the values for which you will get the maximas. Now this is a transcendental equation, and such a transcendental equation cannot be solved using analytical method, and for this either you use computational method to solve this. Here solving means for what value of beta this equation is satisfied. So that's the solution, that's the root of this equation, tan beta is equal to beta. Now for us, we go to the graphical root. What is the graphical root? So let's say this is beta, then what we'll do is, so we have, this is one function, this is another function, and we plot both of these functions separately. So one function is beta, so we plot beta, so it's like y is equal to beta, and this is our y. In different cases y will be different, so this is y is equal to beta, and then we have another function y is equal to tan beta, and we plot that. So how does this tan beta function looks like? Tan beta function is, how much is this? This is pi by 2, 3 pi by 2, then this is 3 pi by 2, 5 pi by 2, and so forth. So if you look very closely, what you see here, there is a solution. How much is this? This is beta is equal to 0, the origin. At this point, this y is equal to beta and this y is equal to tan beta curve is meeting. One point is here, another point is here, and then next point is right here. So what's this curve is telling us? This curve is telling us that at this point y is equal to beta, or at this point tan beta, this curve, yellow curve, and beta, this blue curve, meet. Similarly, at this point also tan beta and beta curve meet. At this point tan beta and beta meet. So these are basically the solution of this equation, or the root of this equation. And then if we find out what are these beta values, these solutions are beta is equal to, one is this trivial solution, another is 1.43 pi, 2.46 pi, and so on. So this is, so beta is equal to 0, that's the trivial, that's like n is equal to 1, n is equal to 0. Beta is equal to 1.43 pi, this is like n is equal to 1. Beta is equal to 2.46 pi, this is like n is equal to 2. So at these values, of beta, you get the first maxima, second maxima, and so forth on the both sides. Now only one thing is left, and that thing is, you find out for n is equal to 1, the first secondary maxima, I is equal to I naught sine square 1.43 pi and 1.4 square. We are asked to find out this ratio. This turns out to be 0.0719, which is nothing but 4.719 percentage. For n is equal to 2, I by I naught is equal to sine square 246 pi divided by 2.46 pi square is equal to 0.01647, which is nothing but 1.647%. So that means as you go away from the central maxima, the first secondary maxima with n is equal to 1, its intensity is only around very close to 5% of the central maxima. For the next secondary maxima, that is n is equal to 2, the intensity is only 1.64% of the central maxima. So in case of single slit diffraction pattern, the diffraction maximus decreases very quickly as you go away from the central maxima. So that concludes our first problem. Now to look at the second problem, the 11th order minima of a single slit diffraction pattern are found at distance of 5 cm on the other side of the central maxima. Find the wavelength of the monochromatic radiation used while the distance between the slit and the screen is 1 meter and slit width is 0.1 millimeter. So here is our problem. First, let us list what are the given things. First thing is 11th order minima. Then it's a diffraction due to single slit. The pattern is found at a distance of 5 centimeter on the either side of the central maxima. So let's draw the figure. So here is a single slit and there is a screen. This is the central line. So the central maxima is here, and then from this, let's say this is the position where the 11th order minima is formed. So 11th order minima, and this distance is 5 centimeter. Similarly, there would be the 11th order maxima here. Then find the wavelength of the monochromatic light used. So we have to find out lambda is equal to what? Distance between the slits and the screen is 1 meter. So this distance is 1 meter. Let's say this is capital D. And the slit width is B is equal to 0.1 millimeter. Slit width 1 millimeter, distance between the slit and screen 1 meter, lambda is equal to what, and single slit diffraction pattern. So condition for minima for the single slit is B sine theta is equal to n lambda. So from here lambda is equal to B sine theta by n. So in the figure, what is theta? Theta is this. How much is the sine theta? Sine theta is, let's say this is OAB. Sine theta is AB by OB. How much is AB? That's 5 centimeter. How much is OB? OB is 100 meter, means D square plus 5 square, and then square root. So from there 0.01 centimeter B and sine theta value, and this turns out to be, this is n is equal to 11 angstrom. So this is the wavelength that was used for the diffraction pattern. Now let's look at the next problem, problem number 3. So this is our third problem. A thin needle is placed at the center of an aperture as in the figure, having width thrice that of the needle. So there is an aperture, and then at the middle of it there is a needle, and the aperture has a width of 3 times the width of the needle. And so here this width, and here this needle when placed at the center of this aperture, creates a double slit. And then it says, if a laser beam is incident normally on the arrangement, so what would happen? Which order spectrum will be absent from the diffraction pattern? So through this double slit, if a laser beam passes through, then it would produce a diffraction pattern. And in that case, which order spectrum will be absent from the pattern itself? Now to understand this, let us now take this problem to our worksheet. So here is our problem, and here we have double slit diffraction pattern. So the intensity pattern is given by, so here this first term is called the diffraction term, and the second term is called the interference term. Why so? Because what happens is, if you have double slits and then there is this laser light coming in, and from this double slit they get diffracted and produce a interference pattern at this place. We'll come how this interference pattern actually looks like. We'll come back to this. This is just a rough sketch. Now from the slit 1 there will be diffraction. Let's say this is our slit 1. Let's say this is our slit number 1 and this is our slit number 2. So from the slit number 1 there will be diffraction, and that diffraction pattern will be observed on the screen. Then from the slit number 2 there will again be a diffraction pattern that will be on the screen. And because two different diffraction patterns are there on the screen, then as a result you will see an interference pattern of the two diffraction patterns. And that's why this intensity expression over here contains these two terms. One, the diffraction term, which is like the single slit diffraction pattern, sine square beta by beta square actually, and then the intensity interference term, which is cos square gamma, where beta is b sine theta by lambda and gamma is d sine theta by lambda. Now what is b? B is the slit width here. This is b, and the slit separation is d. Now graphically, if you look at the intensity pattern that you would see here on the screen, let's say this is S. Here the diffraction pattern over the screen due to these two slits would look like this blue curve over here. If you look carefully, this black curve over here is actually the envelope of the blue curve, and this envelope looks like the diffraction pattern due to just one single slit. And what is this red curve? This red curve is the interference curve. So this black curve is this first term here, the diffraction term, and this red curve is this second term, the interference term, cos square gamma. And when you combine them, then you get this blue curve. So what you see here is that, for example, at the center, the red curve is maximum and also the black curve is maximum. So they coincide, and you get, as a result, this blue maxima at the center. And then the red curve follows continuously as you go away from the center 0. But the red curve, which is the interference term, it decreases oscillatory and increases. So goes from minimum to maximum, minimum to maximum. And that's why the resultant blue curve also fluctuates. But its maximum decreases slowly, and becomes here exactly is equal to 0 at this point. However, the resultant blue curve is 0, but actually the red curve, which is the second term, the interference term, was not 0. It's the maximum. So that means, in a very interesting language, you say that this is the first order central interference maxima. First maxima, second maxima, third maxima, these are all the interference maximas. And these are the diffraction maxima. So this is the first central diffraction maxima. Then this is the diffraction maxima. This is the diffraction maxima. This is the diffraction maxima, and so forth. So blue curve for two slit experiment. These are the different diffraction minimas, secondary diffraction maximas. So the question is asking that which order interference maxima would not be seen. Here, this interference maxima over here is not visible. So this interference maxima cannot show up in the resultant blue curve. However, this does. This maxima produces this maxima. This maxima produces this maxima, and so forth. But this maxima disappears, and so it's asking which order of this maxima is disappearing. So how to find that out? You have to first find out that what are these orders, and then which order of this diffraction minima becomes equal to the interference maxima, and as a result, the resultant blue curve has a minima. So let's proceed. So now, to get the diffraction minimas, this beta must be equal to n pi. Then sine square beta, that would become 0. So that would give us this diffraction minima here. So the first condition is beta is equal to n pi. And this would give us b sine theta is equal to n lambda. So this is the condition for diffraction minima. What is the condition for interference maxima? This gamma should be equal to n pi. So gamma is equal to n pi. And let's say it's m pi, another index. So this is the condition for diffraction minima. This is interference maxima. And when you put the value of gamma, then you get d sine theta is equal to m lambda. Now, when these two match, this minima and maxima match, they match for the same value, sine theta. So along this direction, it's the theta. So that means when these two matches, so we just take the ratio of these two. So sine theta cancels out. What do we get? Take the ratio of the two conditions. We get b by d is equal to n by m. Now, what is this ratio, b by d? If you remember, we had this aperture, and the width of this aperture was 3 times the needle width. So if we say that we have a needle at the center and its width is w, then this width is 3w. So the slit width would be w, and the separation between the slit would be 2w. From the center of one slit to the center of another slit. So this much is 2w. So d is equal to 2w, b is equal to w. So b by d is equal to half n by m, implies m is equal to 2n. So here this n takes 1, 2, 3, 4 and so forth. So this is the condition for all those interference maximas will disappear because they would match with the diffraction minima. So these two conditions. To our slide. Question number 4. A double slit, each slit having width 0.05 centimeter and a separation of 0.5 centimeter between them, forms a diffraction pattern on a screen placed at 1.5 meter away from the slits. If the diffraction fringe width is 0.15 millimeter, find the wavelength of the monochromatic light used. So let's take this to our worksheet. So this is our question number 4. So in this question number 4, what are given? The slit width b is equal to 0.05 centimeter. The slit separation is 0.5 centimeter. The distance between the slit and the screen, capital D, is equal to 1.5 meter. Then diffraction fringe width, beta, is equal to 0.15 millimeter. So as you have looked at in the earlier problem, so this is the diffraction pattern for the two slit. Now what is she saying is that this distance between the maximas, this is the fringe width. This fringe width here, this is beta is equal to 0.15 millimeter. Then find the wavelength of the monochromatic light. So again, here is our double slit, here is the screen. Let's say at some point here, there is this nth minima, and the distance between this and the center is dn. Then from the condition of, so these are the interference minimas. These are the interference minimas, and maximas are these. So the condition for those maxima is d sine theta is equal to n lambda. From here we get sine theta is equal to n lambda by d. Also from this figure, if you like, if this is the theta, then O, A, B. Tan theta is very close to sine theta when theta is very, very small, would be given by AB by, how much is AB? AB is dn. OA is, so we got sine theta here, we got sine theta here. Now they must be same, so that means dn by capital D is equal to n lambda by d. So this is the distance of the nth interference maxima from the center. What would be the distance of the n plus 1th maxima? That would be n plus 1 lambda capital D by small. Now fringe width would be dn plus 1 minus dn. So let's say this is dn, then this would be dn plus 1. So the distance between these two would give you the fringe width. So the fringe width is lambda capital D by small d. So from here lambda is equal to beta small d by capital. From here we would get given beta is equal to 0.15, that is millimeter, small d is 0.5 centimeter, capital D is 1.5, which would be is equal to 5000 angstrom. So this is our result.